Then we're going to just start with some OOP strategies, and we're actually going to like go through and implement some techniques, and the application is going to grow along the way, and we're going to go through and try and solve certain problems, and like we're going to run into certain problems, and we're going to try and figure out some solutions. There's a lot of content, and I've like done this, given the presentations kind of like twice here already, and I know I sometimes skip a little bit, but there will be, even if you don't get everything that I talk about, there's a lot of it here that I'll introduce that you can go and research. So let's just get started. So we're just going to do a simple like class structure. We just have a person and a family class. The person is meant to be pretty simple. It's just got a name, age, a Boolean, whether it's alive, and a nickname, which is optional to just give it a little bit of complexity. The second is a family class, just a surname string, and then it's meant to be very dependent on whether or not we can serialize person. So it's basically got 2 persons for mother and father and a list of person for children. The point is basically to take all of this Scala on the left-hand side and turn it into the JSON on the right-hand side, and just to create a library to do that transformation. We're not going to pretty print because it's just not really the point of the talk. And but let's just get started with some object-oriented design. So nice, simple JSON structure. We're going to start with just an abstract class that's JSON, extend that to Boolean, number, and string, which are just primitive kind of JSON types, and then some complex JSON type for array and object. Everybody's probably pretty familiar with JSON. So let's just jump into some of the code, and I'm going to show you exactly what we've done. So we have a JSON abstract class, and most of this talk is going to be in IntelliJ, like it's actually, the code's here and it runs. So here's an abstract class for JSON. This is pretty basic. Boolean extends JSON, and it's in type, it's got a Scala Boolean. It's to string just to do the stringify. Then we have number, just doing a little bit of logic to print it like an integer or like a floating point, depending on whether or not it has a decimal. String, and just adding some quotes. Array, a little bit more complicated, just mapping over the elements and calling stringify on them. So right now, JSON array takes elements also, which are JSON, and it can take many of these elements because of the var arg star here. And then JSON object, which adds curly braces. It maps over a pair of elements, so you pass it a string and a JSON object. So this is the key and then the value, and there's many of them as well. And then you join them together with comma, and they like come up as comma, like separated key value pairs, and that's it. So the simplest thing we can do is obviously just extend JSON, give our person class a stringify, implement that. We do some isEmpty check on the option of string because it might not be there, and then we create everything by saying new, JSON string, JSON number, JSON Boolean, and passing all of those things in it. And then, yeah, we do it again if the nickname is there, and we give it the nickname this time. So that's like really, really basic, something, you might whip together. And if it's a simple application and a simple structure, that might be fine, and away you go. But being like that, it's supposed to be a JSON library. You probably want it to be extensible. And there's a couple of other things that I feel is wrong with it, and I think needs to be considered. So I'm going to talk about separation of the business model. And basically right now our stuff looks like this. It's got the business logic and the JSON, and they're mushed together because we're actually saying by extending JSON that my person is actually a part of the JSON language, which really doesn't make any sense whatsoever. And so is family, like they aren't part of JSON, so why are we extending JSON? So that's probably the first thing that we could do is just try and like separate those things so that we have obviously some transformation that takes us from our business objects to the JSON objects. And so we're going to introduce a separation layer, which is just a trait JSON convertible. It will define a toJSON method, and we'll just return JSON. So first thing, we're going to seal the JSON abstract class so we can't inherit from it anymore. And then we're going to extend our models from JSON convertible instead of JSON as the first simple thing that we can do. But then this also means we'll have to convert them, and then we'll have to stringify them. So there's going to be a two-step process there. So if we go back to the code, you'll see we'll do just that. We've added a JSON convertible trait. We have our models, and we've had to put them in the same file because we're sealing them, and that's just what you got to do. So we have sealed abstract class, and then everything still extends it exactly the same way as it was. It's just this file instead of all separate. Our person still pretty much the same, except for extends JSON convertible, and we don't call stringify in here. We just return the JSON objects, and then over in main here, we're now calling toJSON and then stringify. This seems like it didn't do a heck of a lot, even like maybe added a layer, but that indirection will become important. So let's see maybe what we want to do next. So if you take a look back at the code again, you'll see that, especially in family, we're able to do like toJSON on any of the person objects, but we can't do that for the primitive objects, and that's kind of like, it seems a little bit off balance, a little lopsided. So maybe we can find a way to do that. So we can introduce a concept called extension methods. So this will allow you to add methods to classes you have no control over whatsoever, and that will, you basically define them as what's called an implicit class, and that wraps the type that we're actually trying to give the method to. It's found via implicit search, which I'll explain in a bit. And it will allow us to give each primitive, like string or int or whatever, toJSON method of its own. And you can define them ad hoc. So even if I didn't put them in a library, somebody who's using that library can actually define these methods on their own. So if they want to add like zone date time or something like that, they can just implement that pattern, and then they'll be able to add a toJSON to it as well. So let's go check that out. So what we've done now is we've added a package object for just the JSON library itself. And I'm going to close this down here. So anyway, oh, actually, sorry, I want to go through some extension method how-to first. So we have a class A, and it's just, you know, has a display method, whatnot. You know, you can call display, and it's just going to print you know, hello on it, and that's it. What if we want to give, zoom that too, and what if we want to give it another display method, so we'll just display two? We can do that, and here's what I was talking about, the implicit class. So I just called it a ops, and it's usually kind of a thing that you name it with the ops of the type that you're trying to do. So it takes in that a as a type, and then you can basically now add the display2 method to it, and you can see I'm just adding a 2. Under the hood, you'll see that what it does is it wraps a ops on A and then calls display2. This is purely Scala magic to do this type of thing. If you notice the little underscore there, IntelliJ will actually tell you where this method is coming from, so that it's not kind of like hidden mysteriously to you, and you can actually like traverse it. So now I can call that on this method, and you know, I can say hello and hello too. Also, just to show you, you can add it obviously to string, and then we can give a string a display method as well, and that works no problem. So now we're kind of able to extend Scala specifically on our own and put our own logic into the actual language. So here is a bunch of extension methods for some of the types we've done. Boolean, int, double, whatever. The sequence one's a little bit more involved. It takes a generic parameter, anything that extends JSON convertible, so whatever's inside actually has to be convertible itself. And then, you can call JSON array, map over the elements, convert them, and then put them in the JSON array, you're done. And then we still have the same program so far. So now we have person and family kind of looking consistent with 2 JSONs on everything. But we're using extension methods for primitives and we're directly extending. So why don't we just switch everything to extension methods and away we go. So here we need to know something a little bit about the way that Scala looks for implicits. First, it looks at the call site. So in main, we're actually going in and importing, actually we're not here. Because this is all within the library, so it's fine. But for the types we define outside, we're actually going to have, we import everything into the main. If it can't find it at the call site, what it's going to do is look at the companion object of the type that you're actually defining it for. So if it's person, it will go to person's companion object, and it will look at there for anything. If it doesn't find it there, it's actually going to look in a higher up. If there's if it extends anything, it will actually look there. So let's check out 4. So no change to main whatsoever. First, I'm going to just show you about the implicit search. So, sorry, let the grow. So we basically start with what we had before. There's no change. We define the implicit class rate in this scope. No problem. Everything runs. It's not a big deal. With the implicit search now, we're going to stuff it in the companion object. We're not importing the companion object, so this is actually hidden from this scope. And you'll see that it's still able to find it. If we indirect it once further, and we're now extending, the companion object is extending this root object here, you can see that still works. But if I remove the extends, then IntelliJ is going to be like, I can't find this method. I don't know what you're talking about. So let's just take a look quickly at person. So now instead of we're doing implicit class in their companion objects. We've now removed it from here, so we're not extending anything on our model objects. Same with family. And it's, looking a little bit cleaner, a little more separated, but still not 100% there. And then there's this, still this JSON object thing going on. And what we really, I think, really want to do is make it so that our models don't know anything about JSON. And we're going to try a first method of doing that, and that's reflection. So what is reflection? It's introspection of the types at runtime. So we can look at a type at runtime, and we're going to take a look at all the fields on that type, and then we're going to try and we can find out their names, we can find out their values, and then we can use that to maybe get rid of this problem, right? So if we should be able to convert each element individually and then wrap them all in JSON object within the reflection method, and then we can remove any knowledge of JSON out of our models. So, so now all of that's gone. From family, from person, the only thing you'll see is that models or main is importing everything from the JSON library. So we then look at here, and we have a new giant, ugly looking method that basically, if you look at it, it's taking what's called a product, which most case classes and stuff extend, which actually allows the reflection to happen. And then we call 2 fields on it, which basically iterates over the fields, gets a sequence of them, zips them with their name, and then it calls this convert on each element within this. So But if you look at this, we've got like cases in all of this. So we've kind of blown our ability to be extensible now. So that's a little bit of a problem, though we did get what we want in our application. You know, it all runs, it's all pretty, it looks really, really nice, but kind of hidden underneath it is a few, like, most of this is at runtime. It's going to slow down your application. And also, you know, and because of that, there's no type safety. The compiler can't tell us that we don't have an implementation. So all we can do is like throw this nasty exception and be like, you know, crash your application, right? So it's not really what we want to do, though it kind of worked in a simple case, and, you know, and sometimes reflections got its purposes, but probably not the right thing here. So we're going to take a little bit of a step back. If you noticed before, oh, and I forgot to, one thing I forgot to show is that we're actually doing option now as well. And I added a JSON null, sorry, I missed that completely. But you'll notice here that all we could say before now is that once we did the extension methods, because we weren't inheriting from JSON convertible anymore directly, that we have to now give it JSON within these objects. So we actually have to convert things within the array, within the option prior to actually, actually it's within the reflection there. So prior to actually converting the array itself. So you see we're mapping with the convert function, and then we're calling to JSON on that. So it's a little bit weird. So it's kind of, but the problem is we can't pull in that type in order to be able to like say, like, how can I convert an integer? How can I convert a string? So there's another pattern, obviously, that lets us do that, and it's a simple change, though it causes a different like pattern to evolve. It's called the typeclass pattern, and we're going to go back and we're going to implement that. So if you've never done FP, you probably don't know what a typeclass is. But it's used in Scala all over the place, so you'll run into it eventually if you've never seen it before. It basically specifies the behavior like that you specify in your trait for a specific type. So it's got a type parameter in it instead of just not having any parameter at all. It's known as kind of ad hoc polymorphism, just basically because like the the implicit class, I can define it anywhere outside my library. But instead of adding methods, it kind of gives you a separate object that has all the methods. And you kind of call it in, and you use that object when you need it. And it's still done by implicit search. So I'm going to check out next version here, and you'll see we've switched everything. I'm going to just do a couple little examples again of the type class pattern. So this displayable, is a type class. You'll see it's just got the A parameter. Instead of like, now the method actually has to take in that parameter. It's not attached to that object anymore. It doesn't contain it or wrap it like the extension methods do. So when I have like my class over here with its internal string, and I want to define the display, I go like down here, I actually have to say, you know, take in my class, and then here's how to print my class. Usually you'll see that there's a separate method that's created for every type class, and this kind of like pulls both of those things in. It pulls the object in and then pulls its type class instance in. So now I can say I want the displayable for the type that I'm actually calling this method on. So here, you know, we could naively implement this and be like my class and then give it the type class instance specifically, but that would be really annoying. Why not use some of the magic of implicits? Sorry, Java people. You know, actually make it so that it passes it itself. So implicit here on the function parameter, and implicit now on the instance. And now all I have to say is display my class. The compiler will go and find this for me, and away it goes. Right? So now it's perfectly functional, prints hello. So next, also just to show that ugly, new yada, 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 because our thing only has one method in it, we can use what's called the single abstract method syntax, and we can define it as if it was like a function. So that kind of cleans up the code a little bit. Also, if you were to create a new function that's, say, called display, but doesn't actually use that, you can actually define this as a constraint within the type parameter to say that it's an A with a displayable, and then it will pass displayable into the function even though it doesn't use it, but then that's required to actually call display. So here, if I run this, no problem, but if I get rid of this, I don't know, so actually it might work. No, okay, it blew up because it can't throw it within the function scope. It doesn't know to do that. So, so now implementing that within the library, we have all of our things as type class instances now. We had JSON convertible as a type class. We also have like a toJSON method down at the bottom with, again, that implicit parameter. So it's going to call converter to JSON. And now we're using everything, converting everything with the toJSON method, the way we go, or the function and the way it goes. Same with family and same with main. So a little bit different. It's a function instead of a method on the objects, but we can probably fix that. We have something in common between all of our types now. All of our types now support this this convertible. So we can define one type class or one extension method that's for anything that has a JSON convertible. So we don't need to do it all over the place like we did before. So then we'll just be able to use like toJSON on everything again, and everything will be exactly the way it was before. So we'll just do that quickly. We'll have just within our package object an implicit class, and I explicitly, just to mention it, use the ugly implicitly syntax, which is there for if you want to use the kind of this type, but you actually do want to use the type class, you can, as they say, call it in from the ether, and it will like materialize that there, and then you can say toJSON on it, and away it goes. And now we're back to our main being toJSON again, and the way it is. So this isn't getting us completely there. We still have JSON objects all over the place. So now we're going to get into a new type of kind of programming that's been out there for a little while, made a little bit popular by that one specific library everybody loves to hate. So I'm going to ask a question. You've got a person type here and a file type, and they look kind of similar. So what's the same thing about these two classes? Well, if you look at them, they have the same types within their fields. The field names are different, class names are different, but they have the same data types. So if these two types having the same data types are said to have the same shape. And what we want to be able to do is kind of just ignore the fact that these classes are different, and we want to be able to deal with their shape itself. So like reflection, we want to be able to iterate over it, but we don't want to use reflection in order to do that. So what can we do in order to do this type of thing? Well, there's a library, as I said, that everybody loves to hate. It's called HLists, and it's a library for abstracting over the shapes of classes. And it's kind of raises functional programming up to the type level, and they call this generic programming. There's three main data types that I'm going to talk about: generic, HList, and I'm not actually going to mention coproduct because it wasn't really necessary for this talk. But generic is used to do the magic of converting between the case class and its generic representation, and the HList is its generic representation. So I'm going to try and demystify the HList a little bit, and hopefully everybody will get it if they have had trouble with it before. It takes a long time, I'm telling you right now, to understand what it is, but I'm going to show you here. So we have a ton of worksheets here because this is kind of a complicated thing. But I'm going to start off simply by saying, well, why don't we just define everything as the tuple type? Like, I mean, it's kind of the same thing. It just doesn't have a name. So you could just say that, like, my file is like a string and an integer, not providing any field names. But I can give functions that, you know, give it the file and I'll give you the string, give it, you know, the file and I'll give you the size. And then so I can create my file and I can say get file name, get file size, and away you go, and it works no problem. But let's take it to the next level. Let's use like the extension methods we're learning about that actually like make it feel like it is the object. We define the companion object. We give it an apply that allows us, like pretend that it's like literally calling it like it's a case class. Now the extension methods have added, these methods to it, so it actually feels like the full object there, right? But there's kind of a problem, and you'll notice if you've ever done like matching on a tuple, you kind of have to deal with the whole thing all at once. It doesn't really like break it off piece by piece. You got to like match the whole thing. So it would be like, and there's like, what size of tuple, right? Like there's, tuple like 1 to tuple 22, and then there's like the empty tuple, which is unit. So like we could be any of those with any of the other classes. So which one is it really? What we want to do is kind of actually like deal with it like it's the list, right? Like we want to be able to like pop its head off, say like deal with that one, and then recursively call ourselves to deal with the rest of the list. And then once we hit the base case, we're kind of done, right? We can just do this recursively. It would be really neat to do it that way. So like, anyway, like, oh, yep, SVT time. So I'm going to show you like Generic uses this thing like the HList to actually give us this kind of behavior. So the weird thing is that it's not just a list at the value level, it's also a list at the type level. And it makes it a little bit weird, and it can be really hairy to work with in some situations, but it's actually got some really interesting uses. So you'll see here, like this type generic file is actually the list of types string, int, and then HNIL. The same way we can define like a list as like ABC2 and then nil, right? So you'll see like file 1, 1024 HNIL is the list at the value level. So it works like a list, but it's not necessarily a list. It's more of a, it's something else, but it's similar. So let's look at like a normal list like this, and I just created my list here, and it's got the normal cons kind of class, and then a cons method for the value level to create the list, and it's got a case object, my nil, and so now I can just create, my list same way, and no problem. The weird thing here, though, is like this doesn't do what we want. We can only put like ints in once we've like specified that, right? Because of this A. Like there's only this one A, and then like I can like the A is like everywhere. So it's like I have a head of A, and then I have my tail is another list of A. So it's kind of locking us in. So let's like wipe that A from the face of the earth, and just like do the simplest thing. Let's just give head as type any, and then like a tail of just type my list. So that allows us to do what we want at the value level, but now all I know is it's like a list. That's it. It doesn't really tell me anything. But the parameters are right. So why don't we like take those parameters and push them up to the type level? So if I was to do that, then like head of any just becomes like H, the type parameter, and then T becomes like T that inherits from my list because it's, we want it to be a list. So we have nothing at the value level now, but look, we can do the same thing at the type level. So now our list is up at the type level, and really all we've got to do is add head and tail back, and we have their type parameters. So like now it's just head is an H and tail is a T, and now we've got the type level and the value level, and it like looks exactly the same, right? So that's really all it is to try and make it the same. So this is called the heterogeneous list because heterogeneous means different parts as opposed to the same parts in a normal list. So I just want to talk about the recursion a little bit, because this is usually the part where like it's like a little bit wacky, and it totally is very difficult to understand when you first see it, but you get used to it. So when you recurse, you have like your base case and you have an induction case. And so your base case is obviously what stops your computation, and your induction case is like, here's the thing I'm going to do. I'm going to call toString, and then I'm going to, call myself with the rest of the list. And then when I come back, I'm going to like, add a comma between these things and whatever. And this isn't tail recursive, it's just normal recursion, right? But if you take a look at that, like it's actually mirrored. It's just a little bit more like, well, a little bit more ugly, I would say. Like instead of just a normal function call, you've got a type class to take the place of the function. And you have like different instances for each of your types. So that's just normal type class pattern, right? But then you still have your base case here. It's just a different method. And then you have your induction case here, which takes like your head and your tail, and then, deals with the head, deals with the tail, and then does the same like concat with, or like with the string, with the comma, right? And then, you can call stringify on that, or you can go up here and, like I've just got join here. But you see they're both doing exactly the same thing. So here's the one with the list, and then here's the one with the HList. So it's a nice example to have like, okay, side by side. So we're going to add this to our implementation. So we have our nil. So one other thing I'm going to mention is we're going to do this as a JSON object. We need to build our JSON object up one by one. So we've now specifically given the JSON object an add method that takes like a key and a value. And so you can just say, start with empty, give it the first key value, and then the next time give it the next key value. That'll allow us to build it up piece by piece. But again, we run into problems. So actually there's two problems here. One we'll deal with first, which is this ugly cast, this as instance of, because our type class, it only says I return JSON, not JSON object. So I've casted it to its parent. I no longer know that it was a JSON object or not, even though if I go through the code, it's pretty apparent that it is. Scala doesn't know anymore, so, that's not very good there for us. But, and also I don't know the name, so I'm just giving everything keys. So if I like run this right now, and actually in main we've got, we're actually just testing with the HList. We're not using our family anymore because we want to just see if this HList works. So we have an HList here. It's all the data from Homer. I didn't mention I'm using The Simpsons as my test data. It does this, but what it's going to do is it's just going to print like key as the names for everything, and it's not going to be all that nice, right? So it's, not very good. But let's not let that stop us. First thing, we're going to get rid of this as instance of thing because it's nasty. So we're going to introduce something called a path-dependent type, which is literally just a type alias. I've shown it already with like the nil. I kind of just glossed over it, but you can just define an alias to whatever types. It means it must be overloaded within our trait, and we actually want to specify the JSON class that we're returning, not just say it's JSON and who cares. So this should help us get rid of the casting in our hcons implementation. So let's go there. So let me show you just quickly a thing about the path-dependent type. So we're just adding this type parameter like out. So I have this converter here, and I just have an int converter, and I have a string converter. And what it's doing is like I can call this convert, with my convert type class, but now the output parameter depends on what the type class has in it. So here it knows like when I give it an int, I'm going to get a string back because I said like, my converter for int returns a string, and my converter for string returns an int. I'm not going to call this with a because it will throw an exception. But now that's not what I wanted to do. I want to hit this one. Now you can see, it knows what it is. It changes the output depending on its input. So we can probably use this you know, except for it's not everything. So it actually doesn't fix the problem yet. But let me show you we have a type, I just call it ENC for encoding type. You'll see that we can't use single abstract method anymore, but we can, you know, Boolean returns a JSON bool, int returns a JSON number, double returns a JSON number, convertible or string returns a JSON string, and so on. The option, you still can't really do anything with it, returns JSON because it could return JSON null or what's in the sum, depends on what you've got. But then HNIL returns JSON object and HCons returns JSON object as well. So we're getting somewhere, but we still didn't get rid of as instance of. And the reason for that is that Scala still doesn't realize it wants like headconf.enc. It's like, I need the output type. It doesn't realize that JSON object is the output type, even though that it is. So we're going to do something else, which is called the aux pattern. And you don't really need the aux pattern per se, but it's just nicer. So basically, like, it doesn't know that the JSON object is the output type, even though it says it in the other method, or in the type class instance. What we need is a way to guarantee they are the same. You can do it without aux, but it just looks like a mess. So aux is really not like a pattern, it's more of just like a thing to make it look nice. And so I'll show you both. So in the first example, you can do this like ugly syntax here. So you can add another type parameter to the convert function, and then you can say that out is, you know, that type. And then that kind of locks it in place. And then, you know, c.out, whatever. So that locks that in place, and it actually will solve our problem. But people don't usually like to write that. It kind of looks like a mess. So what they usually do is in their companion object, they create like this type called aux. And it's just got two parameters, and it uses the first parameter for the type of the type class, and the second parameter for the output type. And then it allows you to just say like converter.aux, like AO, instead of what that nasty curly brace thing had before. So if we take a look here at our JSON, so now what we're able to do is just lock this in as a JSON object, and that completely solved our as instance of thing. So now it's like, hey, wait, no, I'm guaranteeing I'm only going to find type classes with a JSON object output. That's it. So that's problem solved there. So almost done here. One last thing we're going to have to figure out is how to get names. And we're going to do this by kind of annotating the types. And this will be like the weirdest one that I show you, because like note that what I'm going to show you, you won't actually do. It's just how it's kind of done under the hood. It's just to show you the kind of like method that it's actually using in Generic to do this. So what is it? It's not a Java annotation. It's completely different. It's like whatever. In fact, I kind of just gave it this name because I didn't know what else to call it. But we'll use it to add the key names, like I said, to our types. This is done automatically by using labeled generic instead of just generic. But we'll need to figure out how to use it. So we're going to implement it before we start using labeled generic, just within our code. And I can't actually show a worksheet on this one because worksheets won't use macros, and these things are macro-based. So you'll have to, what I've done is implemented it in main, and it looks ugly, and no, this is going to go away. So this witness here is like this weird thing where I'm like actually like passing name, age, alive, and nickname. It's what it is like a dynamic parameter, and it's like a symbol wrapped in this thing, and it's like all dynamic and weird, and then it generates this type, like these macros generate these types for you. So, and I'm just giving them aliases, name, age, alive. So what it does is that you use this like field type, and the first parameter is the key name, and the second parameter is the value type. and what it'll do is like, now that's the type information that's going to go around, right? What it'll end up doing now, so then you like, so under the hood, it's actually like doing this in labeled generic, where it's like field name, Homer, field name, age, 37, and it like, then it generates all this type information for us. So what we're going to see like in the HList is this like field type. So when we go to the JSON, we now have to add a new type parameter for the symbol that we pass with name. That's what that tick was. It's like a symbol, like, so it's like tick name and then tick age. And then during that, we have to call in this witness for that symbol. And then when we do that, because symbols are unique throughout the compiler, even if you define it twice, there's only one of them. So there's only, like, give me the witness for the symbol K. But then you just call, like, value on that, and then, like, as a symbol, you can call .name on it, and we'll give you the actual name of the symbol. And that solves, that part of our problem right there. So now we're actually going to have the names within our, output for Homer here. And one more step, and we've literally got rid of all of this, and that's the generic conversion. So I don't believe, let me just, okay. There's no slide for this. It's just another checkout, because it's not really that big. It's like the last step, so it's like, so all we have to do now is actually perform the generic conversion. So you give it like a generic to JSON. So here's the type we're passing in, and remember I said it has a representation type, so that's going to be represented by R, and that's your HList. So when you call label generic, it's again with the aux pattern. A is your type in, and your HList is your type R. And then I want to find the JSON convertible for that type R, and that has to return a JSON object again. So then, now I can say my encoded type is a JSON object, and then to JSON I can convert to JSON, the generic version of my A, and away it goes. So that actually, works pretty good. I can get rid of everything. If you notice the red over here, IntelliJ ain't keeping up with us. This is too freaking complex for it. It's only the extension methods that do this. If you called like the toJSON function, it's no problem, but IntelliJ just can't hack it at this point. You'll see like in person, family, it's all gone. There's no mention of the JSON whatsoever. We've completely separated our business models from like the fact that they're serialized. So if I go and add XML and I add this and that, I'm not adding new methods. I've got completely separate libraries for each of these things. They don't know about each other. I just call toXML or whatever on them. It's all completely separate, right? Except you notice, there's kind of one thing. I'm calling it on Homer. It's still got a little bit of an issue here. So there's one last thing that we have to do. You'll see this ugly error, and I'll just zoom into the next slide. We can't actually serialize family because of this awful looking error called diverging implicit expansion. Yeah. So what is this? It's like Scala refusing to execute because it's scared. Like, it's just too scared to do this. It won't do it. So why is this? We're going to use like some substitution to figure it out. So like you call toJSON with the Simpsons, and it's like, okay, that's family, and I'm going to use the generic toJSON to like serialize that. So that, is the call, then calls generic toJSON. It's like, here's the family, here's the like generic representation of the family, and it returns a JSON object. Then it's going to like take that representation, it's going to call hcons, it's going to take the first string off, and then it's got the rest of the list, right? Cool. I can get the string, no problem. I call hcons to JSON, oh cool, my next step is a person. And here's the problem. We got to use generic again to do this, right? So then as it's going, it's like, hey, I'm trying to like make this smaller, but then I hit person and it's like, boom. Wait, it got bigger on me again. No. This is going to be like infinite. I'm going to run into like some infinite loop here. I'm not going to do this. I'm going to stop. So we know it's a lie because we know it does work, but what can we do? We have to like do something else, and that's like be lazy, right? We don't want Scala to actually, you know, start doing this until we figured out the entire like type list. So that's what this like lazy function is going to allow us to do. And so we're just going to wrap like the searches for our implicit parameters in this lazy type. And then we're going to call .value on them to actually materialize them only when we need them. So that way you can go and figure the whole type out. And then we'll just materialize it right then and there when we're actually ready to use it. So, oh, sorry. So last thing, 13. What did I do here? Must have done something. There we go. So now it's like literally the simplest change in the whole thing. We just add lazy to these guys on the HList, and then it won't actually, you know, when we get person, it's not going to actually like go and try and find that. Or like it's the type algorithm will work, but it won't actually go and try and like figure this all out until we call value when we're actually within the method. So, and that's it. We now have a working thing. We can serialize the symptoms. I snuck in a nice JSON null match so that we're not spewing nulls into this anymore. And that's it right there. Okay. So it depends on, it doesn't actually work in this case. So if I take it off of the head, it will actually, so I think it's usually the head and that you actually leave it off of, and it doesn't actually, or that you do it on, but if I do it, it usually, like, it doesn't actually work. So I ended up having to do it on both of them. Now it's going to probably call me a liar or something, but yeah. No, there it is. So yeah, if for some reason I had to do it on both in this, I know some of the examples I've seen you actually can, no, that's not right. You can actually do it in, on just one of them, and I think it depends on like how the search is for each of the types, and I'm not 100% sure why mine's different than the cases that I usually see in like, say, type astronaut or something like that. So that was my talk. I don't know if I like, you know, kept everybody with me or not. But all of this is on GitHub. Every example that I was checking out, you can like do that as well. There's, oh wait, let's do this. Oh, you, out of my face, there we go. You'll see that I've got it open here and I've got readmes for all of it, go through and explain the same thing. So it's just that nben's like Scala Talk JSON Write, it's called. Also recommend Type Astronaut's Guide. A lot of this comes from this. It's kind of the same. I wish I actually thought of like kind of a different thing to do, but the serialization one's kind of like the perfect thing for it. And there's also a YouTube version that Dave Grinnell does on there to actually pretty well the same stuff that's in the book. And the book's not really big. It's like actually like, I think only like 20 pages long or maybe even less. So it's actually really interesting. So any questions from anybody else? Go ahead. So there's an implicit function. In the root, sorry, the root class you said? Well, the one for the extension methods, right? Let me just go back. See, and this is why I labeled everything with like example number. So I could just go right back to it. Yes, number 4. So, I'm going to be a jerk now. Okay. So here, so no, it's just not the right one. Yeah, this is it. Is this what you're talking about? That's right. Right, so I just comment the fact that it's inheriting from that root object. So in this case, it has like nothing. It's not a conversion. It's just the way Scala searches for implicits, right? So if I have a chain that's through my companion object, then it just can find that because I'm extending it, and it will just look up your dependent or your companion object's dependency chain and like actually find it there. Yeah. Right, that's right. Yeah, I don't need to like, you know, if I didn't put it in there, like I could put it in a different file, but then instead, like in main, I'd also have to not just, oh, see, and I didn't, yeah, in this one you don't actually import that because all the other ones are within the library, but I would have to import it here if I wanted to use it, right? So theoretically that can be applied to the type class. Yes, that's right. Yeah, and so during the type class stuff, that's what we were actually doing is we put it into person's companion object, right? And then it found it. And then usually you'll see, like, if you want, like, overriding type class instances, you'll see, like, the sooner it finds it, the higher the priority. So then you'll define a more general one in the, like, something your companion object inherits from. Also, like, a really neat pattern called the magnet pattern used by Akka HTTP and, like, Spray all over the place. That, like, does some really interesting stuff with implicits and uses that specifically as, like, a way to, like, overload, what do you call it, like, to abstract overloaded functions, but in a way that allows you to, like, pass it through. So if I have, like, a function that takes, you know, like it's the same function, but it takes different parameters on each of the overloads. Like if I want to call that within a function, I kind of have to, like, and I use that as a function parameter. If I have, like, you know, A takes a string and B takes an int, but they're both called, like, you know, do stuff, then I have to give it a do stuff to, like, map or, like, flat map or something like that. But if I do the magnet pattern, I can give it the magnet version, and what it will do is actually pull in that version once it figures out what the type within the map, like, that it's mapping over is, right? There's some pretty interesting patterns like that. Like, I would definitely recommend, like, these guys keep me honest about it. I'm like, you know, I like to just tinker around with this stuff. They're like, not in this code. If you're going to do it, throw it in a library, right? So, so. Not in a package object. Before it was kind of illegal. So what's Scala version? This is 2.12, but I think you've been able to do it since like 2.10 though. Only in package object. If you declare it anywhere else, just like a common. Oh yeah. So if you do, if you do like classes and stuff in package objects, it complains. Type class instances, like that's why like the type class instance, like type class itself, I define that as like its own like object here, like its own file. But all the instances, they have to be wrapped within an object because they're like their values, right? They'll tell you that it's, what is it, the wrong top of function or something like that if you try and declare them outside like this package object. So they're okay within a package object, but if you're doing like a case class or something or a trait, it doesn't like it. Yeah. Doesn't have what, sorry? Sorry, I can't hear that. What? Oh, macros. So like 2 point. So sorry, this is 2.12, but the 2. So 2 point, like I think it was 2.10 that introduced these like white box macros that Shapeless uses. 2.3, they're going away. Now that doesn't kill Shapeless because the creator Miles Sabin's working with Martin Odersky. What they're going to do in 3, not in Scala 3. In Scala 3, they're going to introduce a new tuple type, and the tuple type will act like the HList. So there won't be like tuple like 0 to 23 anymore. It'll actually be like a list. And the normal way you write the tuple is actually just converted into like open tuple, comma, open tuple, like another thing like that. So, and then they're going to provide the generic conversion as a feature of Scala as well. Also kind of interesting. Oh. Oh, this is, yeah, so this is just IntelliJ, but we have like, the REPL mode, that's just a Scala worksheet. So this is like something within IntelliJ that you can just create a new file like Scala worksheet, and that's it. So you do, yeah, just like right here, and you just create a new one, and then you can just type and away you go. I do like all my stuff in there because it's like way easier than like throwing it in code and compiling the whole application. And the Scala REPL isn't like overly awesome either. So something like people like the SVT, but yeah. He's got all of them, eh?
One more.
Oh, that's a ligature on. It's called a ligature. It's like a special font in IntelliJ. So if you go settings or something, I don't even know where it is. Is it appearance? Where is it? Sorry. Yeah. Where are you? I know. Oh, where? Sorry, come here. Oh, like edit. Oh, sorry, you're right. Yeah. Editor font. Yeah. So no, it's not there, dude. Oh yeah, sorry, yeah, right here, the Fira code 12. Yeah, so this is like a special thing that you can add. It gives you like a whole bunch of like fancy things. Like if I do my arrows, does this. If I do like not equals, I get like that, right? Like so, it just makes it like kind of fancy. And now I like can't exist without it. I'm like, what's the Scala that you're talking about? It doesn't look right to me. So yeah, that's all. All right, thanks a lot, everybody. Thank you.
Have to wrap up. Thank you for coming out. Thank you for staying till the end.